And we spoke more of acids and base last week. So we said, even though we still have reactions to consider, but we will start focusing more on acids and base. And we fully explained that with acids and base, the key things that we look for will be now the theories thereof. So we explained the Arrhenius theory, a base according to Arrhenius theory, and acid according to Arrhenius theory. We also explained now an acid according to Lowry-Brownstedt and a base according to Lowry-Brownstedt. And I said to you, this is now a base of us fully understanding how to identify a base, as well as now how to identify an acid. So a lot of discussion went into this. So kindly check that video and now make sure you fully understand. We further went now to relative strength of acids. When and how do we say an acid is a strong acid? When do we say an acid is a weak acid? So I gave you a clear indication or a definition that we use to say a strong acid ionizes completely in water to form high concentration of H3O plus ions, and vice versa for the weak acid. So I'm just trying to recap. We did now relative strength of bases, also how to indicate whether which one is a strong base and which one is a weak base. We spoke about dilute, and we said dilute doesn't necessarily mean weak, and concentrated doesn't necessarily mean strong. It basically says the proportionality of water is more compared now to the number of moles or the amount of acid or a base that we have. We further moved on and explained conjugate acid-base pairs. But we said for conjugate acid-base pairs, for us to identify, we need to be in a position of fully understanding a reaction. Which one will be my acid? Which one will be my base? And then we explained that in detail. Furthermore, I came across this particular page here. So the lesson of today will start here. We'll start here in a sense that we are building on what is a conjugate base and what is a conjugate acid. So let me take my pen here and say, it says an acid-base reaction involves transfer of protons, and that now it is called protolytic. So what is protolytic? Protolytic basically just says transfer of protons. So if I am going to talk more of acid and base reaction, the concern will be the transfer of proton. And in this case, it's now the H plus. And with this being said, it says I can only talk of acid and base according to Lowry-Brownstedt and according to Arrhenius, where Lowry says an acid is a proton donor. So there's one that is going to lose, which is an acid. And then a base is a proton acceptor. So it basically says the protons in this case are the ones that will be transferred. So protolytic basically just says it is a transfer of protons. But furthermore, when we look into this, a strong acid always has a weak conjugate base. Very, very important. And a weak acid always has a strong conjugate base. Now, let's focus only now on the acid. I have my HCl, HNO3, H2SO4, and HSO4. And we said now my conjugate base of an acid should be one proton less. So the emphasis here is an acid is going to donate a proton. And once it is donating a proton, which is hydrogen, hydrogen, and two hydrogens in this case, and one hydrogen, whatever that is left after donating that is what we call a conjugate base. So I felt that I need now to come up with a better way of making sure that you are in a position of fully understanding what is a conjugate base. So a conjugate base is what is left after an acid has donated now a proton. So if I am looking at HCl, if the H is being donated because we have an acid which is a proton donor, what is left now will be Cl, and that Cl will now become my conjugate base. If I have HNO3 and then it loses a proton, it will definitely become an NO3 minus. And because of that, we will say now it is a conjugate base. So this slide basically emphasizes more on how can one easily see a conjugate base. But let's go now to a conjugate acid. So for me to have a conjugate acid, it basically says I must start with a base. But what is it that a base will do? According to Arrhenius and all the theories, it's now a base is a proton acceptor. So it basically says I am going now to start with a base, but that base must now do what? Must now accept a proton. So a conjugate acid will be one proton more. If you check now the OH in this instance, which is a base, it says if it is going to accept a hydrogen, then it is going to form water. So basically, water is a conjugate acid of OH, OH minus. And it should be now, because it's a conjugate acid, it must be one proton more. Fine. So this is just to emphasize on conjugate acid base pair. Now, moving to this other bullet here, it says a strong base always has now a weak conjugate acid. A weak base always has a strong conjugate acid. So these are type of questions that you will get in your multiple choice. And with multiple choice, we'll definitely write our test very soon. It will always be online, but it's questions that you find now in multiple choices. It's questions that now emphasizes whether we talk of strong or weak acid still. But when do I know that I am working now with a strong acid? When do I know that I am working with a weak acid, strong base, and weak base? So I compiled a list. Manuku,
Dumela ntate.
dumela mme.
Ntate kopa ho botsa moo ho Antonia CO3 2 minus. What do you think got 2 minus here?
CO3
2
2
minus.
minus. Okay. What happens is, remember, the 2 minus basically represents the number of electrons that will react. Ne? So now, if that is the case, if I am gaining one proton, I'm basically saying I am canceling off one other electron. So that is the reason why it is also changing. Let's look at HCl. HCl, because I am donating a proton, which is a plus, I'm going to be left with Cl minus. And it is key here, like I said, is protolytic. The H plus, the Cl minus, and O3 minus, they are very, very, very important for one to have. Because if you miss the HCO3 minus here at the top, it basically says that cannot be a conjugate acid of CO3 2 minus. So basically, what am I doing? If I am gaining protons, it basically says my number of electrons now is becoming more and more. It means I'm going to move towards becoming more positive, because a proton brings now about a positive charge. So it means if I am a base, let's look at this one. HCO3 minus. If I bring a proton here, it is making this substance to be neutral. Because of what? Because of now adding a proton basically says I am reducing the number of electrons, or basically increasing or decreasing the charge to become now more positive, because I am increasing greater number of protons. I hope it's clear, Manu. Thank you very much. Now let's move on to a point where I wanted to say, if I am working with a strong acid, weak acid, strong base, and weak base, remember we said we need to have this information here of relative strength of acids, to say if they tell me that I am working with a strong acid, it is going to ionize completely in water to form higher concentration of H3O plus. That is the first thing. If they tell me now, giving me in terms of the names, I can also be in a position of identifying which ones are strong. So it basically says I must know which ones are strong. Then I emphasize the issue of Ka value. If the Ka value is greater than 1, that acid must be a strong acid. So I compiled a list of the basic ones that we need to know. Ladies and gentlemen, you need to know relative strength, which is here. And you also need now to know the formula, as well as the name of. Because now one examiner can easily say we have a reaction of hydrochloric acid with water. So you need to know the formula of hydrochloric acid and that one of water. In multiple choice also, the question can come, is HCl a strong or weak acid? They did not give you that statement that says it ionizes completely. They did not give you the Ka value, but what do we know? We know now from the general science that now these ones here will be strong, and you can assign Ka value which will be greater than 1. And these ones here will be weak. Definitely we know now the Ka will be smaller than 1. And what is Ka? I explained. Ka is just now an ionization constant of an acid. So if that is greater than 1, it makes it strong. Because I want to say, they can even give you the concentration to say the concentration of this one is 2 mole per decimeter cubed. It will still be strong. They can give you 0.5 of this mole per decimeter cubed. It will still be strong because the science only gives us an opportunity of saying it is now what? Strong acid. But when we talk of dilute, it becomes a different story completely. So these are the key acids that I want you now to take into consideration. The names, formulas, where and the relative strength. Is it weak, strong, or yes, is it weak or strong? Because we are going to need this moving forward. So I'm going to give you guys 15 seconds. Let's make it 20 seconds to digest everything that we have done so far. If there are questions, also remember to raise your hands. Thank you very much. There are no hands in the chat. So it basically says everything is fine. So remember the names, formulas, strong or weak, very, very important. So these are the basic ones that the examiner wants us to know. And I compiled this one also. This one is examples now of strong and weak bases. So these are the base by the name sodium carbonate will have that formula and it will be weak. Sodium carbonate will have that and will also be weak. So let me take a hand from Fumani. Yes, Fumani.
Hello, sir. I'm sorry to disturb, but could you please go back to the table of the strong
Acids.
acids one more time?
Okay.
Yes, please. Just want to take a screenshot.
Oh, you want to take a screenshot?
Yes.
There's no need because you are going to get the notes thereafter.
Oh, okay. Thank you.
Thank you. Remember the notes, guys, will still be available immediately after the session, but because I want you to listen to me attentively such that we don't miss anything. So let's go back now to this table of strong and weak bases. So they say yes, sodium hydroxide is a strong base. So I repeat, this you just need to learn. If it gets complex, they will tell you something about Ka value, Kb value. But for now, it will be best, it will assist for this lesson if I say this is weak, this is strong. Because it brings me now to what the examiner wants us to know. So these are acid base reactions. These ones you need to know by heart, unfortunately. So this, we say NB to them. These ones, NB, very, very important. Very, very important. Because you need now to know if I have HCl reacting with sodium hydroxide, it will give me salt plus water. If I am working with an acid, but it reacts with a carbonate, let's say here it's a carbonate, it will give me now the salt it will give me now the water. It will also give me carbon dioxide in a form of a gas. So these are key because you are going to be expected and asked for you to complete this type of reaction. So I'm going to clean it quickly for you such that when I send out the notes, you definitely know wow and how is it going now to look like. So please be in a position of fully understanding exactly these equations as they are. So with these equations, believe you me, the examiner can ask anything and everything. But as much as it says write down the neutralization reactions of common laboratory acids and base, we write them in such a way that we perform what we call acid base titration. So let's talk about acid base titration. Acid base titration. So one will ask, what is this titration? So I'm going to give you a definition of what is titration. And we just say titration is a procedure, for determining the amount of acid, or base in a solution by determining the volume of a base, of a acid or base of the known concentration that will completely react with it, full stop. So let's highlight key things. Is a procedure. That means it is an experiment that we can perform in a laboratory. But why? We want to determine the amount of acid or base in a solution by determining the volume of either acid or base of the known concentration. Very important. That will now completely react. So this says to me, it is an experiment that we need now to know. But we have now what we call the apparatus for this specific reaction or titration. So I'm going to include the apparatus, sort them out, and indicate to you what each one will do. Let's add this one, and this one. Now let's try just to arrange them accordingly. We'll make this one, put it somewhere here. Take this one, put it somewhere here. Take this one, increase the size and lock it. Okay, this one is fine even if we don't lock. So these are the apparatus that we need. So I'm going to try and label each one of them. This one here, we call it a burette. So basically a burette is the one that you can use in terms of measuring the volume that we are interested in. Because it clearly says we need now to have some form of information that relates to this specific amount of volume. It's the burette as the first one. You need to know that. And then you have this one here. And this one is called a retort stand. Retort stand. You must also know that. Now, this one here, most people call it Ellen Meyer flask. It's Ellen Meyer flask. So these are the apparatus we need for titration to take place. But let's go back to the definition again. Is a procedure for determining the amount of acid or base in a solution by determining the volume of an acid or a base of the known concentration. So a key thing here, it says now we must have what we call a standard solution. So the standard solution is this one that comes now with the known concentration. So in simple terms, a standard solution is now what? A solution with precisely known concentration. Precisely known concentration. 100%. So what does this say? It says now, key thing, known concentration. So around the burette and the Erlenmeyer flask, because that is where my liquids are in. There has to be one with a known concentration. And that one with a known concentration is the one that we say it's a standard solution. So next time when somebody asks you what is a standard solution is now a solution with a precisely known concentration, a solution of precisely known concentration. So we know everything about it. We know the volume. We also know the concentration. So, but now in this apparatus of mine, where do I put my standard solution? So my standard solution should be now in a Erlenmeyer Allen-Meyer flask. So in the Allen-Meyer flask, I'm going to have our standard solution. That one I need now to know. But furthermore, what volume are we determining? Is a procedure for determining the amount of acid or a base by determining the volume of an acid or a base. So it basically says the only way of me measuring the volume is through the burette. So the burette here is going to assist me in terms of measuring the volume of the unknown substance. That is why we have now the burette. We precisely know the concentration of the standard solution, but we now use the burette to measure the volume of the unknown substance. But if I don't have anything here, let me duplicate this so that we create more space. If we only have this, it means I will forever be putting more of the unknown solution, more of the unknown solution, more of the unknown solution. So it's not going to assist me anyhow, and I'm not going to be in a position of measuring or knowing how much of the burette do I need or the unknown solution. So I'm going to clean this up such that now we add on number 2. Okay. Fine. Let me see if I can't highlight this and move it up a little bit. Nice. Beautiful. Now, we know what is titration. We know what is standard solution. We know why the burette is there to assist us and allow us to measure the volume of the unknown solution. But if I don't have any way of having a situation where I can say I have added enough of the unknown solution, then it means this reaction will take forever and ever. So what do I need? I need something that will assist me in terms of the color changes. So once I have added enough, from here maybe to here, that is now my volume. Let's change it to yellow also for purpose of emphasis. 100% looks nicer now. So if I don't have something that will indicate to me that I have reached this part of completely react with it, then it says I haven't done anything yet. So what do I need here? I need to add something else. And that something else that I add here, it is called an indicator. So what is the purpose of the indicator? Or what is an indicator? Fine. Let's write it down. What is an acid-base indicator as number B? Acid-base indicator. A dye used to distinguish between acidic and basic solutions by means of the color changes it undergoes in these solutions. So that is the reason why we need to have an indicator. So an indicator is there to assist and help us to distinguish between acidic and basic solution. But how does it do that? It will give us a color change. So once I am now pouring in my unknown substance, it will be in a position of helping me to fully understand now what. When it starts changing color, it basically says now I have reached my end point. So this will now give me what we call an end point. So that will be now at number C. And at number C, I'm going to write here to say end point. These are new words that each and every one of us must now know. So what is an end point? An end point is the point in titration. The point in titration where the indicator changes color. So it is a point in titration where the indicator changes color. Very, very important. So for me to say my reaction is now complete, it means it has reached an end point. So how do we tell of the end point? By the color changes. What do we need? An indicator for that. So I'm going to give you 30 seconds for you to digest all these. And ask questions thereof. Siamo. Raise your hand again, please. Yes, you can talk, Tiam.
Sir, can you explain again for the indicators again?
Okay. Now, while you are still on the platform, remember we have two solutions here. Ne? Solution number one is the unknown solution that is in the burette. The second solution now is the standard solution. So if I am going to pour my unknown solution in the Ellen Meyer flask, I'm going to pour most until I don't know when. So the indicator is there now to give me that you have added enough. So it indicates a point in titration where now my solution is no longer acidic, it's no longer basic. Remember, acid-base titration, one will be an acid, one will be a base. So we basically want to neutralize everything. So if I don't know of how much acid do I need or of how much a standard solution I have, then it basically says it's pointless for me to perform this particular experiment. So the indicator assists me to be in a position of an understanding that I have added enough acid, so I am now at my end point. That is the reason why we need an indicator. Imagine if you have HCl, which is colorless, and you have sodium hydroxide, which is also colorless, and you just mix the two. It basically says we have a solution that is colorless. But how much of an acid did you need to neutralize this? We did not know, or we do not know. So we add an indicator for us to be in a position of changing colors. So once the color changes, it indicates now what? The end point of titration. What is the end point? It is the point where now the acid and okay, let me just say the solution is no longer acid, it's no longer acidic.
Basic.
Yes, or basic, yes. Are you fine, Siam?
Yes, sir. I will say yes.
Okay, no, thank you very much. And then I'm going to mute you now and just lower your hand. So let's finish the 7 seconds then. Thank you very much. Besides Siamo, it says everybody is fine. So what else do I need to know? Obviously, I need to know the names now of the indicators that I need. So I'm going to add a new sheet. Let me copy this one and delete everything in it. The next slide is going to be very, very important. It's a slide that I feel if you understand that, you can answer each and every question that comes your way. So let me delete everything in here to create space. To create space. Then we are good to go. So this will be now my number 4. It will be on indicators. My life is to make your life, especially the physical science life, to be very, very easy. And One will ask, how am I going to do that? I am going to say, this is my beautiful princess. And this beautiful princess of mine has A and B. But what is this? What is it that I have written here? It says to me, the first one will be methyl orange. Methyl orange. This one will be bromo thymol blue. And then this one will be phenol sorry for that, phenolphthalein. Sorry. Phenolphthalein. But how is this assisting me? What I want you to get from this slide is the MBP, my beautiful princess. So for me to work with methyl orange, I need the solution to be acidic. For me to work with bromothymol blue, I need the solution to be neutral. For me now to work with phenolphthalein, I need the solution to be basic. But how does one create a solution that is acidic? How does one create a solution that is neutral? How does one create a solution that is now basic? It says to me, I must use strong strong acid that will react now with a weak base. So I need to have, my pen is flat. Let me quickly connect it to the charger. There we go. It's strong acid must react now with a weak base. Remember, we said we must have now an acid and a base. So, but that first line that says strong acid plus weak base, it says basically I need to go to that table that indicates to me which ones are strong and which ones are weak. So if this is the case, that reaction is a strong acid and a weak base, the solution will be acidic and the relevant indicator will be methyl orange. But for me to use bromothymol blue, it says I must have a reaction of strong acid plus strong base, or even weak acid plus weak base. So if that is the case, then I'm going to get a neutral solution. The relevant indicator should be bromothiamol blue. But when I look at phenolphthalein, which says now the solution should be basic, what do I need? I need strong base plus weak acid. And this now definitely, it guarantees me that when I come to this option of which indicator will be relevant. So for instance, if in here I have now HCl and in here I have sodium hydroxide, what is the relevant indicator that I need? The relevant indicator that I need is for me to remember the MBP, my beautiful princess, methyl orange, bromothiamol blue, phenolphthalein. Acidic, neutral, and basic. But for me to get an acidic solution, I need what? Strong acid, weak base. But if it happens that I have strong acid, HCl is a very strong acid. Sodium hydroxide is a strong base. It means the relevant indicator must be now bromothiamol blue. Going to give you 30 seconds for you to digest everything in here or on the slide. I don't see any hands. So it basically says everybody is now happy with this particular slide. I'm going to repeat. MBP for my beautiful princess who always have A and B. So this beautiful princess entirely reacts depending on what is the two things that are reacting. So if I have a reaction of a strong acid and I have a reaction of a strong acid and a weak base, the solution will be acidic. When you move further, because I did say this chapter or topic overlaps to grade 12. When you move further, we'll add issues of pH and everything like that. Then you will understand why the pH of the solution is now lower towards 0. It's because of the reaction thereof. It's a reaction between a strong acid and a weak base. Did we use a relevant indicator? Yes, which is methyl orange. So the examiner also wants us to know. Let me copy this and delete. So after copying this, we can say, let's select this and move it up a little bit. Let's move it up to here. So these are my indicators. But the examiner says, if one needs to know the type of indicator that one needs to know. We also need to know the color changes thereof. But what are these color changes? Color changes, very easy. Remember, this is my beautiful princess. So God blessed us now with nice 3 beautiful babies. So the firstborn was Mary. Okay, let me just write color changes. A, indicators, B, color changes. So the first one was Mary. The second one was baby. The third one was Tupac. You can raise your hands and ask questions. So my beautiful princess, MVP, who always had A and B. God blessed her with now 3 beautiful kids by the name of Mary, Baby, and Tupac. But in that number, how does this now relate to the science? Very easy. Because we said MBP. So it says if I use methyl orange in an acid, it will change now to red. I repeat. If I use methyl orange in an acid, it will change color to red. But if I use methyl orange in a base, it will change now to yellow. So let me highlight this information. If I am using methyl orange, the M for methyl orange, the A for acidic, the solution will be red. But if I use methyl orange in a basic solution, it will now change now to yellow. This is very, very important. These are key questions that the examiner always asks. So R for Mary. The M is for MVP. If I am using methyl orange in an acid, it will change the color to red. If I am using methyl orange now in a base, it will change color to yellow. But now what if I'm using bromothiamol blue? If I am using a bromothiamol blue in an acid, it will change color to yellow. So let me highlight that and use now yellow again. But if I am using bromothiamol blue in a base, it will change color to blue. It will change color to to blue. Ladies and gentlemen, this is very, very important. Very, very, very important. If I am using phenolphthalein in an acid, it will be colorless. But if I am using phenolphthalein in an acid, in a base, it will change the color now to pink. I am trying to find the pink here. Pink is something like this. It will change now. Does this look like pink? Yes, it looks like pink. It will change now to pink. Ladies and gentlemen, I'm going to unmute all of you for the purpose of you saying something. I'm going to try and assign you a mic. I want us to discuss something here. So let's give you this. You can unmute yourself if there's something or anything that you want to say about the slide. Comment anything. Mapani Hope, you can unmute yourself. I give you a mic this time.
Sir.
Yes, Mr. Mapani Hope.
Good evening, sir. Ke batla ho botsa ka ntho ka bromothiamine blue in a neutral solution. In a neutral solution, what's that?
In a neutral solution, remember, it's going to be a reaction between strong acid and a strong base. That will result in a neutral solution. Ne? So if the solution is neutral, the mere fact that we are using bromothiamine blue, if I'm going to add bromothiamine blue in a container of an acid, that acid will change from colorless now to yellow. But if I'm going to take the bromothiamine blue and add it now into the base solution, remember the base is also colorless. So it's going to change now from colorless to blue. That is a way of saying this solution, first one, because I used bromothiamine blue and it changed from colorless to yellow, then it means it's an acid. And the second one now changed from colorless to blue, then it means it's a base. That is how now we can use indicators also to identify which one is an acid, which one is a base. Yes,
Okay,
Mapani.
sir.
Okay. Thank you very much. But
no, you still on to
okay, basically you are saying your question is, if the solution is neutral, then we use bromothiamine blue.
Color.
What will be the color
change?
Thank you.
Yes,
there will not be a color change. There will not be a color change. The reason for that is, remember, in a form of a titration, we want that neutral solution to be there. So it basically says we just need to have an indicator that will assist in that regard. So if you take bromothiamine blue and you add it in water, no results. It will just stay the same color as it is. But now if in this point you want to classify which one is an acid, which one is a base, it's easy because the other one will be yellow, the other one will be blue. But if the solution is just neutral, then it basically says we don't have any form of an indicator that will assist us with that. So the bromothiamine blue will not necessarily change the color of that solution. I hope I tried to answer you. Thank you very much. Any other one?
Thank you, sir.
Thank you, Mr. Mapani Hope. Any other one? Maybe I should also give you a timer so that we know that we are still within the time frame. Remember, after this, I'm going to take now the mic away, so you'll not have any chance to say something. So I'm giving you 40 seconds for you to digest the slide. Thank you very much. So no one wanted to say something, so it basically says we are good now to go. So moving forward, we started here saying this is an experiment that we want to perform. So if you are going to perform this experiment, remember we said we wanted to determine the amount of an acid or a base in a solution by determining the volume. So it means somehow we need to have a form of a calculation that will assist. So to have that, it says to me, there need to be an equation that I can use. So this is the equation here. I'm going to try and rewrite it for the purpose of explanation. It says Ca, sorry, let's choose a pen and black. It says Ca Va over Cb Vb is equals to Na over Nb. So basically, if you check that, it says we need to get the mole of an acid. We need to get the mole of an acid. Mole of acid. But where do we get that? From the balanced equation. It says this one here will be now the concentration of acid and the other one will be volume of acid. So the SI unit in this case does not matter. Can be in decimeter cubed, can be in centimeter cubed. It will really not have much of an influence on your answer. Just remember the volume that you, the SI unit you used is the same SI unit throughout. So what does this say? Looking at the statement that is given, it says during a titration, 6.5 centimeter cubed of dilute HCl neutralizes exactly 25 centimeter cubed of sodium hydroxide solution. If the concentration of sodium, HCl is 0.2 mole per decimeter cube, calculate now the concentration of that. So which one is our standard solution in this case? HCl is a standard solution. I'm going to write it here to say HCl is a standard solution. Why is it a standard solution? Because, ladies and gentlemen, precisely known concentration 0,2 and precisely known volume. So a standard solution, I repeat, is a solution with a precisely known concentration. So we know the volume, we also know that. So it becomes a standard solution. Fine. Now, calculate the concentration of sodium hydroxide. So basically, sodium hydroxide now is an unknown solution. So it says, if I were to set up the apparatus like this, then in my standard solution in this case will be the HCl. And my unknown substance in this case will be sodium hydroxide. So that is the reason why I said, even if the examiner asks you which one will be a standard solution or where or which apparatus consists of a standard solution, we are in a position of doing that exactly. So let me remove this and go back to the question. Now, the only thing that I can use here is this thing that we call titration equation. So this, we call it titration equation. So let's use it and check what will be our final answer. So I'm going to give you 2 minutes just to quickly do this one. Kindly send your answers now to the chat. Just 2 minutes. Kindly send your answers to the chat, and then we'll discuss it in the next 2 minutes. It said I only got 2 answers. Remember, guys, we are working against time, so we must always try to do things the right way. I got an answer from Marshall Vilagazi, 0.052, and then Tsiamo Obakeng, 0.052 mole per decimeter cubed. Let's confirm and see if that is true. Okay. Basically, Marshall, your hand is up, so let me give you a mic. Yes, you can talk, Marshall Vilagazi.
Okay, good evening, sir.
Evening, Mr. Marshall.
Yeah, so I realized that I could possibly have made a mistake. I see that it is 6.5 centimeters cubed. So do we have to like convert that?
Not
In this case?
necessarily.
Really?
Yes, I will explain now.
Oh, okay, sir.
Thank you very much. Okay, let me try and explain. It will be, change the pen to black. It will be CAVA over CBVB, which is just equals to NA over NB. But something now becomes wrong already because I need this from a balanced chemical equation. So if I do not have a balanced chemical equation, it basically says I'm going to make a lot of mistakes. So what is it that I know? HCl will react with sodium hydroxide to form now sodium chloride plus now H2O, and it must be balanced. So when I check the ratio thereof, it looks balanced already. So I can easily say the concentration here of the acid that I have is 0.2. So I'm going to quickly write that down. 0.2. The volume I have, I can leave it as 6.5 centimeter cubed. It's not a problem, provided that the volume of the base is also in the same SI unit. But if 6.5 centimeter cubed is given for HCl, and this was now in decimeter cubed, you will be now in a position of converting one of the two. So basically what I'm saying is the volumes in this equation must be in the same unit. If they are not in the same unit, then you must now convert one. So these two must be in the same SI unit. Must be in the same SI unit. So because now the 6.5 is in the centimeter cubed and the 25 is in centimeter cubed, it's fine. We can leave it now as is. Then divide that by, we want the concentration of the base, CB, the volume thereof that was given was 25, which is now equals to 1 over 1. 1 over 1. Where do we get 1 over 1? It's the molar ratio from the balanced chemical equation, comparing now the two there that we have. So this basically says it builds now from the stoichiometric calculations that we did a couple of times ago. So basically, this is now the approach. Let me get my calculator quickly. So for my calculator, I'm going to have 0.2 multiply by 6.5 divided now by 25. It will give me something like 0.052 mole per decimeter cubed. So CB is equals to 0.052 mole per decimeter cubed. Then I am happy with the solution. I am happy with the problem. I fully understand when and how to use the equation. The key thing was, let's emphasize into looking for the same SI unit, especially for volume, because the only SI unit we have for concentration is mole per decimeter cubed for our syllabus. So, but for volume, you can have it in centimeter cubed, decimeter cubed, liters, milliliters. Just emphasize, just ensure that your volume is in the same SI unit. So if you're working with decimeter cubes, let it be decimeter cubes for all of them. If you are working now with what is this? Centimeter cubes, then let it be in centimeter cubes. So now the time here is exactly 20:29. I'm going to give you 40 seconds to digest today's lesson, and then we'll be in a position of saying our goodbyes. Remember, you must now write your reflections on this session, comment, write something in the chat such that I can be in a position of having something to write for my report about this lesson. So I'm going to give you that 40 seconds, and then after the 40 seconds, okay, I see their hands up. Let me pause the time. Okay, let me start with Siamo. Siamo, you can talk.
Yes, sir. Regarding question Marshall, then the concentration is measured in moles per cubic decimeters, whilst Refueka cubic centimeters. So ne ke botsa for how to convert, like what Marshall asked.
Sorry, big brother, there's no need for one to convert. The only thing that will influence the answer is, let's say, the volume of HCl was in decimeter cubed, ne? And the one of sodium hydroxide is in centimeter cubed. So it basically says you now have two different SI units for the volume. So it means you're going to get it raw. But because you're working with centimeter cubed and centimeter cubed, it's fine. There's no need to convert in this instance of titration equation. But if it was 6.5 decimeter cubed and the other one is 25 centimeter cubed, you'll have now to convert one. Either you move from decimeter cubed to centimeter cubed, or from centimeter cubed to decimeter cubed. So basically, hence I am emphasizing here to say, that the volume must have the same SI unit. Marshall Vilagazi? You can talk, sir.
Yes, sir, I was going to also ask you about the answer. I feel it's somehow confusing because we used centimeter cubed to calculate, and then our answer was somehow that answer, but yet still the SI unit stays moles per cubic decimeter. So aren't we supposed to first convert the our answer we got to decimeters first, and then we get our answer?
Let me
That's
do
when
it
we could
for
use
you
the SI
on
unit.
let me do it for you on the board to show you why there's no need. Ne? Just check your screen quickly. This year, oh sorry, let me get a pen. We to write it in red. This one here, it is mole per decimeter cubed, which is the SI unit. This one here, it is centimeter cubed. And this one here is also centimeter cubed. What does that say to me? It says to me this and this will cancel. And then I'm only left with that.
Oh,
It is the mathematics.
oh,
Thank you very much.
oh. Hey.
So I'm going to give you, are you still asking, Mr. Marshall?
Oh no, sir, I'm satisfied. Yeah.
Okay, no, thank you very much. So I'm giving you that time I promised you. Let's wait for this one to finish and then we can close the session accordingly. Don't forget your feedback. It's highly needed. Where to improve, what not to do, and how best can we be in a position of ensuring that we get the desired quality of teaching. And remember, the videos will be available on my YouTube channel, which is Nambane Academy. Thank you very much. And from me to you, if there are no questions on anything, kindly have a beautiful evening.